Hello, my name is Panova Irina. I'm an engineer at the Nuclear Safety Institute of the Russian Academy of Sciences. I would like to introduce you my presentation, Spatial Kinetic in Fast Reactors. To perform calculations in tight kinetics of fast reactors, a special software at the time code was created to solve transient neutron-transport equations in a 3D hexagonal geometry in a multigroup diffusion approximation. These equations take into account 8 groups of delay neutrons and their spectrum and a source of external neutrons. A transient problem is solved through several algorithms. The code also can solve an inverse kinetic equation using calculated or experimental signals. The code has a modular structure, which is into a shell. Our calculations show that in the fast reactors, delay neutrons in the spatial kinetics have a significant effect. Any perturbation into the reactor is reflected in the fractions of delay neutrons. For example, if we deal with a positive reactivity, the fraction of neutron groups with short half-life increases, whereas the fraction of the remaining groups decreases. As a result, effective parameters of reactor kinetics are changed. In this figure, we can see a plot of reactivity variation following a control rod stoppage. A real experiment lasts about 200 seconds and then a signal is stifled by noises. But the code allows to see the reactivity changes till they're approaching the values which were calculated for a stationary state. Thus, asymptotics of some transient processing in the fast reactors is determined by the asymptotics of delayed neutron processes and equals hundreds of seconds. In the operating reactor, control rod actuates in the case of reactor runaway. However, efficiency of control rod is calculated for the stationary state. In this figure, we can see a plot of reactivity variations for a standard method of control rod efficiency measurements for 2 experiments. A control rod starts to move from stationary state, and a control rod starts to move after a prior reactor runaway. As a result, we have differences of reactivity estimates more than 5%, because the reactor has different asymptotics for these 2 cases. Experiments on the big physical tanks of the IPPE confirmed these results. The code allows to solve the optimization problem of selecting a point for locating a sensor, wherein the sensor efficiency in the calculating experiment would vary in the minimal possible way. For example, in the longitudinal direction, the best sensor location place is found in the middle of the channel. Calculating a reactor safety, an input of reactivity should be modeled as the point having most unstable time behavior. For this purpose, the code allows to estimate a shape of the third harmonics, which you can see at this figure. It has alternating signs with 2 extremes in the areas of height gradients of the zero harmonic inside the cross. It is likely that the reactor areas wherein perturbations will provide the longest passing to the asymptotic state can be estimated using the third harmonic extremes area. Thus, the time code can solve a lot of problems in the safe justification of fast reactors, and I thank you for your attention.